Welcome. Today we start with the second lecture on learning. In the last class, we had given an introduction to machine learning. Today we will look further at the problem of concept learning, and in the subsequent classes we will look at some machine learning algorithms. The instructional objectives of today's class is as follows. We will be reviewing concept learning or classifiers. We will look at more closely into the inductive learning hypothesis and explain the various types of inductive bias, and also discuss why inductive bias is required to select a hypothesis. We will look at the definition of aversion space. We will discuss the concept of overfitting, and we will also look at the issue of cross validation in order to find out the accuracy of a classifier, and we will look at some versions of the aversion space learning algorithm. So, in the last class we have talked about concept learning or inductive learning for classification. This problem has already been introduced to you, and let us review the problem again. So, the assumption is that you have a goal concept, that is that you are trying to learn, and we call this a target concept. And as we discussed, the target concept could be something like description. You want to know whether a given object is an apple or not, or you are given an image, you want to know whether this is an image of 0 or not. So, your objective is to learn a description of the target concept, and what you are given is a set of examples which we call the training set. An example or an instance X is described. So, an example or an instance X is described by a vector of features also called attributes. For example, suppose X is an instance. X consists of n values x1, x2, xn. x1 is the value for attribute 1 for this instance. Xn is the value of attribute n for this instance. So, for the learning problem, we have a number of attributes or features, and each instance is described by its value for each of these attributes. Our training set consists of a set of such training examples. And there is an underlying labeling function f that maps an instance to a class. Sometimes we will be interested in two class learning problems. In those cases, we will say that some of these instances are positive examples of a class and negative examples, others are negative examples of the class. So, there can be two classes, positive and negative, or in general there can be a finite set of k classes, and each instance is labeled to belong to one of these classes. So, f is a function which maps an instance to one of the classes from 0 to k minus 1. Now, our objective is, given a set of training examples, that is a set of instances x, and for each instance its label fx which is given to us, we want to learn the target concept f. The function f is not known to us, but we know f applied to the training instances. So, we guess an f, we guess something which can possibly be f, and these guesses are called the hypothesis that we form. So, we talk about a hypothesis space. So, we are going to search for f, and where are we going to search for f? We define a hypothesis space. Once we have decided what are the attributes or features that we are using, we will define a hypothesis space, and the hypothesis space is a collection of possible hypotheses. We will try to find a good hypothesis out of those in the hypothesis space. So, the hypothesis space H is a space of all possible hypotheses H1, H2, Hn. So, H1, H2, Hn are the different hypotheses in the hypothesis space. So, the set of hypotheses, there are many hypotheses H1, suppose there are n hypotheses H1, H2, Hn, and we want to find one of these hypotheses which is possibly close to the target concept f that we are going to learn. Now, it may be the case or it may not be the case that the target concept f is exactly one of the hypotheses in the space. So, if you do not choose the hypothesis space well, or if the hypothesis space is not expressive enough, the target concept f may not belong to the hypothesis space. Nevertheless, your objective is to find a hypothesis of the hypothesis space which is close enough to the target concept. So, the objective of the learner is to find a hypothesis H, small h, which is a member of the hypothesis space capital H, which fits the training data the best. Now, we will see what we mean by fitting the training data later. So, in order to identify a good hypothesis or the best fit hypothesis from the hypothesis space, the learning algorithm has to carry out some form of search through this hypothesis space, through the space of possible hypotheses. Now, the learning problem, this concept learning problem is schematically represented in this figure. So, we decide a hypothesis representation which defines the hypothesis space H. The way that we are going to represent the hypothesis defines the hypothesis space. We will talk a little bit about this presently. And our objective is to find the desired hypothesis by searching from this hypothesis space. And the desired hypothesis is one which best fits the training examples that we are given. The training examples are input to the learning algorithm. The learning algorithm searches through the hypothesis space to find one of the hypotheses which best fits the training example. Now, how do we get the hypothesis space? You see, we have got a set of attributes or features, let us say A1, A2, An are the possible, are the n attributes. So, the hypothesis space is defined in terms of these attributes, and the representation that we choose to represent the hypothesis defines the hypothesis space. For example, if we consider that a hypothesis is a rule, and so it is a simple rule where the with a rule which can be expressed in, let us say, predicate calculus, and the antecedent of the rule is a conjunction of literals. So, that could define an hypothesis space. So, suppose that we have three features A1, A2, A3, then what are the possible hypotheses? The possible hypothesis could be A1, A1 is a possible hypothesis, A2 is a possible hypothesis, A3 is a possible hypothesis, A1 bar is a hypothesis, A2 bar is a hypothesis, A3 bar is a hypothesis, A1 and A2 is a possible hypothesis, A1 and A2 bar is a hypothesis, A1 bar and A2 and A3 is a hypothesis, and so on. So, we can find out the number of such hypotheses. These are the possible hypotheses, and we want to find one member of this hypothesis space that fits our training example. Now, if we consider a different class of hypothesis, suppose our hypothesis is at disjunction of exactly two literals, then our hypothesis space will be different. What would be the possible hypothesis in this space? A1 or A2 is a hypothesis, A1 bar or A2 bar is a hypothesis, A1 or A3 is a hypothesis, A2 bar or A3 is a hypothesis, and so on. So, we will have a different set of hypotheses. So, the attributes that we use and the way that we represent the hypothesis, represent a rule, determines the hypothesis space. The hypothesis could also be described in other forms, which we will, some of which we will study subsequently. For example, the hypothesis can be represented as a decision tree, the hypothesis can be represented as a neural network, and so on. Now, some more definitions let us review. A training set is the set of all training examples that are given to the learner, and on the basis of the training set, the learner forms the hypothesis. Now, after this hypothesis is formed, this hypothesis has to be evaluated. Now, if you evaluate the hypothesis using the same examples on which you have trained, you are likely not to get a good reflection, because your hypothesis may try to fit the training data perfectly well, but they may not work well for other data that you have not seen. So, it is good if you can use a different set of examples for testing. So, the set of examples that you use for testing is called the testing set. So, these examples in the testing set should ideally be not known to the algorithm before it has learned the hypothesis. So, the testing set is the set of all examples given to the learner after it has learned the hypothesis. This set is used to test the accuracy of the learned hypothesis over the unseen examples. Now, so let us say that this oval represents the set of instances, set of all possible instances, and as you know, instances are described in terms of the values of the attributes. So, these are all the instances. Now, a concept is a subset of the instance space. So, only a subset of the instances belong to the concept class. The other instances do not belong to the concept class. So, the concept can be represented as a set which is a subset of the instance space, and our objective is to learn this concept. Now, we find a hypothesis, and this hypothesis in general may not be exactly the same as the concept. So, when we have a hypothesis, we see that there are some examples which are correctly classified by the hypothesis. For example, these examples are correctly classified by the hypothesis because they are positive according to the concept, they are also positive according to the hypothesis. Whereas, if you look at these examples, for these instances, they are actually members of the concept, but they are not members of the hypothesis. So, these are called false negative instances. Similarly, these instances, they are classified as positive by the hypothesis, but actually according to the concept they do not belong to the concept. So, they are called false positives. So, this is the region of false negatives, this is the region of false positives, and the middle they are labeled as positive by both the hypothesis as well as the concept, and the rest of the instances are also labeled as negative by both the concept and the hypothesis. So, these are the two regions, the false positives and the false negatives are the two regions of error for the hypothesis. So, now our objective, as we said in the inductive learning, is given a set of training examples, we have to learn a description or we have to learn a hypothesis. And as we have noted that we cannot learn this deductively because we do not have access to information about all the instances. We use the principle of inductive inference. And the inductive learning hypothesis states that any hypothesis which is found to approximate the target function well over the training examples will also approximate the target function well over the unobserved examples. Now, let us see what is the assumption behind this. Now, if the training set and the test set belong to the same distribution, so if they are similar, if there is some similarity between them, then by looking at the training set, if we can identify a pattern, we can infer inductively that such a pattern actually exists and it will be true of all instances. So, this is the principle of inductive inference which helps us to make an inductive leap. And also, as we discussed a little bit in the last class, now you are given a set of training examples. On the basis of the set of training examples, you want to learn a hypothesis. Now, there could be several competing hypotheses. Now, what is the basis on which you decide which of these hypotheses to choose? Because you see, the hypothesis that you should choose is the one which has the minimum error, which is the highest accuracy, but you cannot measure the true accuracy of the hypothesis because you do not have access to all the training examples. Therefore, you must use some sort of bias which is called inductive bias. There are many biases which have been used. For example, simplicity of the hypothesis is a possible bias. So, a learning task is not always well formulated. So, there could be many functions which are consistent with all the training examples, and the algorithm must choose an inductive bias or must have an inductive bias on the basis of which the algorithm will decide one of the hypotheses. There are several types of bias that could be used. There could be a bias while designing the hypothesis space. So, as we discussed, the set of hypotheses is defined by the hypothesis space, and hypothesis space is defined by the data structure or representation that we use to describe the hypothesis. So, by restricting the language for the hypothesis space, you have a restriction bias. Also, given a hypothesis space, even in this hypothesis space, there could be several competing hypotheses. Which one of them would you choose? You will choose based on your preference bias. For example, you might say that if I have a rule which has only whose size is 1, I will prefer that rule to a rule with size 3. So, I might say that I might prefer a simpler hypothesis. So, we might have also a preference bias. So, there could be two types of biases: restriction bias, which restricts the hypothesis space, and preference bias, which selects among the possible hypotheses in the same hypothesis space. So, in hypothesis space restriction bias, we restrain the language of the hypothesis space. For example, we might consider the hypothesis space of monomials. What is a monomial? Monomial is a conjunction of positive or negative literals. So, monomials is a conjunction of literals. We might say that our hypothesis space must only be a monomial. For example, A1 and A2, A1 and A2 bar and A3, A1 bar and A4 and A3, and so on. So, these are examples of monomials. If we have a monomial, we cannot have disjunctions, right? We cannot have hypotheses like A1 or A2. We cannot have hypotheses like A1 or A2 and A3. So, if we decide that our hypothesis space is the space of monomials, we are ruling out other types of hypotheses. So, what is the advantage of choosing a restricted hypothesis space. So, if you have a smaller hypothesis space, the process of learning will be simpler. The number of hypotheses that we have to search, the size of the hypothesis space is smaller and the algorithm may be simpler. The disadvantage of choosing a small hypothesis space is that a small hypothesis space may not capture all hypotheses, all possible hypotheses. So, it may not be able to express all types of hypotheses. If we take an unrestricted hypothesis space, we can represent all types of functions, but then there will be a lot of functions which are consistent with the training examples, and we have to give a strong preference bias to choose one of them, and trying to search from a large hypothesis space, we will not get a good algorithm to do that. In preference bias, we try to use a bias to decide which hypothesis is more useful. There are several types of preference bias which have been considered. One very popular type of preference bias is called the Occam's razor principle. So, Occam's razor is a very old principle, and it means actually that things should not be multiplied unless it is necessary. So, what it translates to is that we prefer simpler formula for our hypothesis. So, if you have two competing formula and one is simpler, we will prefer them, and there is some intuitive explanation of Occam's razor. If there is a simple pattern, you see there are the fewer simpler hypotheses, simpler patterns than more complex patterns, and if a simpler pattern can fit our training data, it has a better chance of fitting unseen data. And a second type of preference bias, which is also very similar, is the principle of minimum description length, or MDL, which states that the best hypothesis is the one that minimizes the total length of the hypothesis and the description of the exceptions to the hypothesis. So, these are some of the biases that people have used. Now, when we have a set of competing hypotheses, so when we have a hypothesis space which consists of a set of hypotheses, how do we search for the hypothesis that we want? The search could be carried out in many ways. So, we will just mention two simple possibilities. One possibility, you consider only one hypothesis at a time which you call your current hypothesis. Now, if the current hypothesis is not good enough, you choose another hypothesis which is your next hypothesis. So, this is a previous hypothesis and you try to go to a neighboring hypothesis using some operators. So, we could use certain operators, like we could try to make the hypothesis general or more specific. So, this is the sort of the search of our current best hypothesis search looks at one hypothesis at a time, and if it goes to a point where there are no good alternatives, it might backtrack to a previous choice point. So, several algorithms have been suggested to do current best hypothesis search, but the thing to note is that unless the hypothesis, if the hypothesis space is very large, this search will take a long time. The other type of search which has been advocated for theoretical learning algorithms is least commitment search. Least commitment search considers multiple hypotheses at a time. So, it maintains a set of hypotheses, set of possible hypotheses, and as it gets more training examples, it tries to restrict this set of hypotheses or maybe add some more. So, one type of such algorithm uses the notion of what we call a version space. Suppose our original hypothesis space is capital H, and capital H consists of n hypotheses H1, H2, Hn. Now, when we see an example, some of these hypotheses are consistent with the example and some of these hypotheses are not. If we remove those hypotheses that are not consistent with the examples, we get the remaining hypotheses which are consistent with the current example. So, the hypotheses which are consistent with all current examples constitute the version space. As we look at more examples, the version space is further restricted. So, our algorithm might maintain the current version space, and as it sees more examples, the version space can get slowly restricted. This is called version space learning. So, a hypothesis, so more formally, a hypothesis H is consistent with a set of training examples D if and only if Hx and Cx or Fx is the target concept that we are trying to learn. C is a target concept. So, if a hypothesis H agrees with the target classification C for every training example that we have seen, then that hypothesis is consistent with the training example. In other words, H is said to be consistent with the training set D if for all instances x Cx belonging to the training set Hx is equal to Cx. Okay. Now, what is the version space? The version space, which is denoted by VSHD. So, version space with respect to the hypothesis space capital H and the training set capital D is the subset of hypotheses from the hypothesis space that are consistent with all the training examples. This is called the version space. So, in other words, version space VSHD is the set of all small h, all hypotheses belonging to the hypothesis space such that it is consistent with the training set. Now, with this definition, we can outline a simple algorithm, theoretically simple algorithm called the list then eliminate algorithm. In list then eliminate algorithm, initially we take when we have not seen any examples, when D is null, we say that a version space is the entire hypothesis space. So, we list all the hypotheses in the hypothesis space. Then as we take training example one at a time, we throw out all the hypotheses which are inconsistent with that training example and then we continue. Now, this algorithm is very simple to describe, but actually it is unrealistic because usually for any reasonably complex hypothesis, the hypothesis space is really large and it is not practical to store all the hypotheses in the hypothesis space. Nevertheless, the list and eliminate algorithm can be theoretically described as follows. We maintain a data structure called the version space, which is a list containing every hypothesis in the hypothesis space initially. Then we process each training example one at a time. We remove from the version space any hypothesis inconsistent with the current training example. And at the end, we output the list of the hypothesis remaining. So, this is the basic version space algorithm. And obviously, as you can see, this algorithm is not practical because the number of such hypotheses is very large. Now, we will just briefly discuss a variation of this algorithm, which instead of keeping the entire list of consistent hypotheses, tries to represent them in a succinct manner. So, a version space can be represented by keeping a list of all consistent hypotheses. Additionally, a version space can be represented by keeping the set of general hypothesis and a set of hypotheses. So, you see there are some hypotheses in the hypothesis space and there are inconsistent hypotheses. These inconsistent hypotheses are either more general than one of the hypotheses in the hypothesis space or more specific than one of the hypotheses in the hypothesis space. And in many cases the version space can be succinctly represented by a set of most general hypotheses in the version space and by the set of most specific hypotheses in the version space. Any hypothesis will belong to the version space if it is, so the specific set is called the S set, the general set is called the G set. If a hypothesis is less general than one element of G set and more general than one element of S set, then the hypothesis belongs to the version space. This is the idea, and with this idea an algorithm called the version space algorithm or candidate elimination algorithm has been formed, which maintains the G set and the S set. However, we will not go into the details of this algorithm in this class. Now, let us see what we mean by choosing the best hypothesis. You see, we are given a set of training examples, but our real goal in learning is to find a hypothesis f dash belonging to H that will correctly classify new examples, all examples. So, the ideal thing would be to choose that hypothesis f dash that minimizes this probability, the probability that f dash misclassifies the concept. So, f is what we are trying to learn, f dash is what we have. So, we want f and f dash to be very close, but we cannot compute this probability because we do not have all the cases with us. Now, how do we measure the success of a learning algorithm? The measure is, we have to measure how well the learned hypothesis predicts the classification of unseen example. Now, how do we evaluate therefore a classifier? So, we have to measure the predictive performance of the hypothesis. You see, if we learn on the basis of a training set and we test the performance on the same set, we are cheating in some sense, because our hypothesis may very well classify the training set, but may not do so well on the test set, because we have already seen the training set and we can be biased towards the training set. Therefore, in order to make a better judgment of the accuracy of the classifier, we must measure it using unseen examples, and this set of unseen examples is called the test set. And to the extent possible, we must keep the training set and the test set disjoint. Now, when we test the accuracy of the classifier, we will get some sort of curve like this. So, what we expect is, as the size of the training set increases, the accuracy of the classifier may increase. So, we plot on the y axis the accuracy of the classifier, and we measure the accuracy of a classifier on a test set which is disjoint from the training set. And as we include more and more training examples, we plot the accuracy of the classifier. So, we may typically get some curve like this, and the accuracy may increase or decrease as the number of training sets increases. So, this sort of curve is called a learning curve. Now, so we want to fit the hypothesis to the training data. So, we are training examples, we have some training examples, we have a space of possible hypothesis, and we have an error function, and we try to find a hypothesis which minimizes the error function. Okay. There could be several error functions that we could use. For example, our error function could be the number of examples which have been misclassified, or our error function could be the sum of squared errors between f x and f dash x. Now, you see, if you test the accuracy on your training data, you will usually note that as you train more and more, the accuracy on the training data increases. However, as if you try to go on increasing the accuracy on the set of training data, what might happen is that the accuracy on unseen data increases up to a point and then reduces. So, this is a common phenomenon that you can observe, that as you train more and more, as your algorithm is tuned more and more, the accuracy on the training set may go on increasing, but after a point the accuracy on the test set may decrease. So, this is a typical behavior that you might notice with many learning algorithms. And what is happening usually is that your algorithm is overfitting the data. It is fitting itself to all the idiosyncrasies in the training data, and which makes it incapable of generalizing over unseen data. So, this phenomena is called overfitting. Because more you train, the better you fit the training data, ultimately all the examples might be memorized. If there is any noise in the training data, you see, the data that you get may not be a pure data, there may be noise in the data. For example, suppose the color of an apple is green, it might appear as yellow. So, if you try to fit in the noise in the training data, the algorithm will overfit the training data and work very well on the training data, but it will not work well on the test data. So, this is an example to illustrate overfitting. These black things here are the training examples, and you see that the curve that you have got fits all the training examples. The green balls are the test data, and you see this curve does not fit the test data very well. It has 0 error on the training data, but it has some error on the test data. For the same examples, we have another curve which has greater than 0, which has some finite error on the training data, but it fits the test data in a better fashion. Now, so how are you going to properly test the accuracy of your classifier? You are given a set of examples. Now, what you should do is that instead of using all the examples for training, you should keep aside some of the examples for testing. So, you hold out some of the examples. The total examples that you have, you divide into two sets, the training set and the test set. On the basis of the training set, you train your classifier and then you measure the accuracy with the test set. So, the holdout method advocates splitting the available data into two sets. The training set is used to train the classifier. After the classifier is trained, the testing set is used to estimate the error of the classifier. Now, one standard technique which is used. So, of course, this holdout method requires that enough number of examples are available, so that even after keeping aside some data for the test set, you have enough data remaining to use for training. You know that usually for most algorithms, the more data that you use for training, the better you can expect the accuracy of the classifier will be. So, this sort of holdout will only work well if there is sufficient amount of data, but sometimes what happens is that a lot of data is not available. In certain fields, it is not very easy to get data, and in those cases you have to use your judgment, you have to use some intuition to optimally use the data that you have. So, one of the techniques is called the k-fold cross validation. In k-fold cross validation is useful when you do not have a large amount of training data. So, what you do is you partition the available data into k classes. For example, this is a case of 4-fold cross validation. We have divided the data into 4 classes. and then we ran 4 experiments. In experiment 1, we keep aside the first class for testing and the remaining 3 we used for training. In the second experiment, we keep the second data aside for testing, use the remaining 3 for training, and so on. So, we have 4 experiments, and for each experiment we get an accuracy, and we estimate the accuracy of the classifier as an average of this accuracy. So, this is called k-fold cross validation. It could be used to conserve training data and make best use of the training data. And one extreme case of k-fold cross validation is leave one out cross validation, where if you have m data, you divide the data into m sets of one example each and you run m experiments. In experiment I, you leave aside one of the data I, you use the rest for training, and on the trained data you test one. So, this sort of approach is used when you do not have a large amount of examples available to you. So, in k-fold cross validation, the true error estimate is obtained as the average of the different, you have k estimates of error and you take the average to obtain the average estimate of the error. So, leave one out cross validation, as I have already mentioned, it is actually often you will see it being referred to as LOOCV. LOOCV stands for leave one out cross validation. It is a case of k-fold cross validation, where k is chosen as the total number of examples. So, if you have a data set of n examples, n experiments are to be performed. For each of these experiments, one example is kept aside for testing and n minus 1 examples are used for training. Now, let us look at questions based on today's class. So, question number 1, suppose you have a 2-class learning problem. So, the classes are plus and minus. The classes are referred to by Q. So, Q is the target concept that you are trying to learn, and you have got 7 different examples, and there are 4 attributes to this learning problem: A1, A2, A3 and A4, and all these attributes are all Boolean attributes, and you have got these 7 examples. So, you assume that there is a bias in favor of simpler hypothesis. So, your objective would be to find a good hypothesis for this particular concept Q. So, the training data are, please note down, first example true, true, false, false, it is negative. The second example is A1 is false, A2 true, then false, true, its class is negative. Third example, false, true, 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 class positive. Example 4, true, 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 false, class is positive. Example 5, false, true, 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 class is positive. Example 6, false, true, false, false, class is negative. Example 7, true, true, false, true, class is negative. So, given these examples, you try to find a simple hypothesis for Q, and you can also try to find several hypotheses which are consistent with these training examples and find the simplest of them. You use your own measure of simplicity. Question number 2, again we are giving you another training set. Now, this training set is slightly more complicated. We have again 4 attributes: A1, A2, A3, A4, and we have a target concept Q. Now, we have to, so again for these training examples you must try to figure out different hypotheses and propose one of the hypothesis which is a possible good hypothesis which describes or which is consistent with all the training examples. Okay. So, here again we have 10 training examples. Example 1, A1 is high, A2 is red, A3 is in, A4 is NV and classification is positive. Sample 2, A1 is high, A2 is green, A3 is out, A4 is V, classification is positive. Third example, A1 low, A2 green, A3 in, A4 V, Q is negative. Example 4, A1 is high, A2 is red, A3 in, A4 NV, Q is positive. Question 5 or example 5, A1 is low, A2 is green, A3 is out, A4 is NV, Q is negative. Example 6, A1 is low, A2 is red, A3 is in, A4 is V, Q is negative. 7, A1 is high, A2 is red, A3 out, A4 NV, Q is negative. Example 8, A1 is low, A2 green, A3 in, A4 NV, Q is positive. Example 9, A1 is high, A2 is red, A3 is in, A4 is V, Q is negative. Example 10, A1 is low, A2 is blue, A3 is in, A4 is NV and Q is positive. So, your exercise would be given this training examples, find some competing hypothesis and choose one hypothesis. Then last question, question 3, you state whether true or false. A, overfitting is more likely to occur when the training set is large. B, a hypothesis is found that achieves 80% accuracy on the training set. The hypothesis is guaranteed to have a lower accuracy on any test set. State whether true or false. Whether the accuracy on any test set will always be lower than the accuracy on the test set. Now, we have come to an end of today's lecture. We will, before we stop, we will discuss the answers to the questions that we posed yesterday in the last class in lecture 33. Question number 1, consider the problem of trying to recognize handwritten digits. Formulate this as a concept learning problem. A, clearly specify what can be the possible features. B, how do you get the training set and the test set? C, how will you measure the performance of your learning algorithm? So, let us look at the answer. So, in order to recognize handwritten digit, what is the input that you get? The input is an image. Suppose you write this digit 1 or write this digit 7. The input is an image containing this digit, and in this input usually when you are trying to recognize digits, this image will be in only black and white or only in two colors, the background color and the pixel color of the digit, right. So, from this image your objective would be to find out whether this is a 1 or a 7 or a 2 or 3 or so on. So, your raw input is an image in, let us say, JPEG or bitmap, etc., from which what you can get is the pixel value, right. So, you get the pixel value and you can do some sort of image processing, so that you ultimately get a black and white image. So, you binarize it and you get a black and white image. So, some pixels are black, some are white, and from this image you want to know the identity of this digit. So, the raw input is the set of pixels. How many pixels? That will depend on the size of this window. Suppose this window is 20 pixels by 20 pixels. So, you have 400 pixels, each pixel is either white or black. This is the raw image. Now, you can try to get a hypothesis using this raw features. So, you see, if you use this raw features, your algorithm may not be able to get a good hypothesis unless all the possible ones are written exactly in the same way. Some people might write a 1 like this, some people might write a 1 like this, some people might write a 1 like this, some people like this. So, all these have different pixel representations. Okay. Now, if you want to do a very good job of recognizing these digits, maybe it will help if you can extract some more sophisticated features from this raw image that is available to you. For example, you could try to find whether there is a vertical line. You can try to look at the image and you can try to detect all vertical lines in the image or all possible lines in the image. You can try to get several different transforms, you can find the moment of the image. So, you can get a set of more sophisticated features which can be used by your learning algorithm. So, the raw input to this learning problem is a set of pixels, either white or black. Actually, initial input is an image which consists of colored pixels. After you do some pre-processing or binarization, you get some raw pixels, and you can further make it more sophisticated by getting more sophisticated features. For example, the value of the first moment, the result of half transform, the different lines that are present in the image, or you can use different masks. So, those are the inputs to your learning problem. Now, how would you get the training set and the test set? So, to obtain, so if handwritten digit recognition is the problem that you wish to address, you should get several of your friends or to write down the different digits in their handwriting. So, different people may write different digits differently. So, if you get different possible digits from different friends, you can try to use these as your training set or the test set, or you could take certain places where you have access to handwritten digits. For example, you could if you are at the post office, you could scan the pin codes that people have written by hand on the letters and try to recognize those digits. So, you collect a set of such samples, and once you have collected sufficient number of samples, you use some for training and the other for testing. Now, to measure the performance of your learning algorithm, you use a training set on the basis of which you learn your classifier, train your classifier, and evaluate the accuracy on an unknown set, the test set. Okay. Now, question number 2. Consider the problem of trying to play a game of Ludo. Formulate this as a learning problem. Clearly specify what your system will try to learn. How can you get the training examples for this system? Now, in order to play a game of Ludo, in order to learn to play a game of Ludo, there are two things that you could do. Either you could work it out in the supervised learning framework, or you could work it out in the reinforcement learning framework. We will not be dealing with the reinforcement learning framework really in this class, but it is good to be aware of this framework. In supervised learning framework, you might get a set of database of boards, and for this board, for every roll of the die, in Ludo, you know, there are at least 2 or more players. Suppose there are 2 players, let us make the thing simpler. You have 2 players, player 1 and player 2. So, when it is your turn to play, the board, there is a board and the different pieces are in different positions, and you roll a die. Depending on what roll the die turns up, you have to play your move. So, basically what you are trying to learn is, given the board and given the die, given what move you have got, what is the move that you should take. Now, in order to learn this, if you have a set of training examples where for different board positions and for different rolls of die, you have the recommended move to make given by an expert, then you could try to learn the move from the board. However, this set of, actually you need a really, because in Ludo the number of possible board configurations is very large, and for each configuration you have several possibilities of what the die throw turns up. So, the number of possible situations is very large, and this is not a very easy learning problem, unless you are able to generalize in some sense. Okay. So, using this raw features is not really very practical. So, you have to generalize the board in some manner. Now, the second way that you can learn is by, you can play games, play automated games against each other by random moves, and you can generate a huge number of database of such games, and you can use reinforcement learning to learn. Okay. So, we will not talk about this right now, but even in the first case, what you really need to do is to, in order to make this learning program practical, the raw board configuration is not very easy to deal with, because there are so many raw board configurations. So, to handle games like chess, Ludo, backgammon, where there are so many configurations, what you try to do is, you try to get certain features from analyzing the raw board. For example, the features could be number of pieces of the opponent which are in home, number of pieces of the opponent which are in unprotected situations, whether your die roll is able to capture an opponent. So, like this you can decide, you can set up some features. So, if you have some features, let us say 20 or 30 features, then for your current board position you can evaluate the values of these features, and then from the examples that you have, you can abstract them in this feature space. For each instance you can find the values of these features, and then you can see what is the possible move, and from this you can learn. Okay. So, we stop here now. We will, in the next class we will go to a learning algorithm. Thank you.